So, hello. What are we going to do today? We're going to talk about the xv6 part of the project. For those of you new to kernel programming, which might be most of you, the xv6 part, especially at first, might be a little strange. It's a code base that's 5,000 or 8,000 lines of code. I forget how big. So that's not nothing. That said, it's not a million lines of code. So a student who's an enterprising student could actually just sit there and learn the ins and outs of the xv6 code base. And one way to look at that is that means you could get an entire working operating system into something that into your brain, right? You could understand most parts of it. So that's kind of cool. That's why we use it in class instead of some big real thing, quote unquote real. How many people have already built and run it? All right, all 6 of you. So, well, time is ticking, and the one thing that this class does not wait for is projects. Like I said, when one is done, the next one comes out. So I understand hey, we have that nice weekend before the project is due, and I'm sure you're all canceling all your weekend plans in order to spend time doing the project on that weekend, but be wary of doing that. It's good to do a little bit early. Even if you don't do a lot early, it's good to do a little bit to make sure that you have some sense of how to do it. That said, once you get into this project for today, this won't be a super challenging one. If it is super challenging, it's going to be a very bad semester, is one way to look at it. And I'm just trying to be honest. So you can't say I didn't warn you. It may be a bad semester anyway because you really hate this class or you're taking a lot of other bad classes or whatever. But if the first project is hard, you should come talk to me. And I will, if you do badly on the first project, I will actually find a way to drag you into my office hours and talk to you about it too. So there's another incentive not to do poorly is you have to talk to me if you do poorly at the beginning. Because if you're doing poorly at the beginning, it's really going to be, like I said, a long semester. Okay, so I'm here on my machine running a shell. I'm actually, some people ask, you can see here I'm on a Mac, I'm using this thing called iTerm. It's a great terminal program. It lets you do all sorts of cool things like easily create new windows and stuff like that. And it's very fully featured. And getting good at a particular terminal and shell environment is worthwhile, especially if you're in the C Unix world at all, which some of you would be, as you go off to do whatever you do. But I'm going to log in from here into one of those Mumble machines. You can, of course, go sit at those machines and do this project, but you can also just log in like I'm doing. One key feature here, you may or may not be familiar with the many flags of SSH. For example, I'm sure most of you don't spend your night reading the SSH man page, but if you do, you'll see it has a few options. You'll be quizzed on these at the end today. And this is a really important one. It's -X. Or capital Y works too, which basically enables X Windows traffic. X is this thing that was developed many, many years ago at MIT to enable computers like the earlier versions of this one to have like Windows and the beginnings of a graphical user interface. And it's still used today, amazingly. And when you log into a machine remotely, you want to be able to forward the X traffic that's generated there to the screen here, and the way you do that easily with SSH is with this dash, say $X. If you don't do that, when you try to run QEMU in the default graphical mode, it'll complain that it can't find a video terminal or something like that. And maybe if some of you have tried it, may have noticed that already. So please log in such a manner. This is where I always feel nervous, typing my password just in case I'm somehow focused on something else on the screen, and then I end up typing it in the plain text. That hasn't happened yet. I'm sure it'll happen at some point. At that point, I'll immediately upload this video to the internet and see what happens. Okay, so what we'll do here is, what I'm going to do today specifically, now we'll get into more technical stuff besides my random general advice ramblings, which I'll do occasionally too, so you're kind of stuck with that, is what we'll do is we'll basically just unpack the kernel, we'll build it, and then what I'll do is I'll walk you through a system call. We're going to walk through in great detail what happens on a system call. And the first project, well, what is the first project in xv6? Does anybody remember, roughly? Yeah.
Build a system call?
Well, yeah, it's adding a system call. What does it do?
Add a counter?
Yeah, it's like a real primitive system call that, so somewhere in the kernel you're going to count when system calls take place, and then this new system call that you're adding is going to go and get that number out of the kernel and give it back to like a user program. So that's often it's a classic startup project in any kernel is, do you know how to add a system call? It's harder than adding a function call to a program that you write, like a user space program, because the kernels are sensitive about things like system calls. They don't want arbitrary programs calling into them in arbitrary ways. They want to be very controlled about that. So we're going to learn about that process in some detail. Okay? So in class we learned a few things. Let me make a directory somewhere. Sorry. Discussion, xv6, intro, let's call it 13. So we learned about system calls at a conceptual level. What do we remember about that? A, they exist. Okay. B, they're called system calls. Okay, easy questions I've answered. What is a system call? Like when I'm talking about a system calls, somebody asks you about what is this? Hey, your parents call up. Hey, I heard about these things called system calls. What is going on with that? This is probably not likely to happen. By the way, I used to think that your parents would never talk to you about things like computers even, or like, the first day I saw a billboard that had a URL on it, I'm like, oh my God, normal people are going to know about this stuff. It was terrible. Yes?
System calls when you like ask the kernel to get some sort of information that's usually like privileged, like an IO call or something like that.
Yeah, you want the kernel to do something on your behalf. Instead of you can't just do a function call into it, because if you can function call into the kernel, you can basically take over the machine. So there's a barrier erected between you and the OS. The OS can do things. It's privileged. It controls the machine. You as a user program are not privileged, but you can ask the OS, and if the OS says, oh, I like you, in other words, oh, you're a certain user who has certain privileges, it'll let you do certain restricted things, like read your own files, for example. Okay, so and that means there's some hardware machinery we're going to have to understand and look at. And this kernel is built for x86, which is a widely known architecture, which means we're going to learn, when we learn specifics here, what we're going to learn about is the specifics of x86 and how it provides support for system calls. Make sense? So how many of you have looked at x86 assembly code before? I know a few of you have, because I taught a version of 354, which you took, where we looked at x86 assembly a lot. In future, like I said, future versions of 354 will have a lot of x86 assembly, which is of course completely useless to most of you. So you're welcome for that. Okay, so the first thing we're going to do is we're going to untar the actual stuff that we have here. So it's in this directory. So if you do, tar is like, it's useful to know some various flags. If you do tar with a T and not an X, and then these are like, it's verbose, and this means that the thing is zipped and whatever, then what this will do is it'll show you what tar is going to do if you use the T flag instead of X, and that way you can know, is it kind of, what crazy thing's going to happen when I do this? You can see it's saying these are all the files I will unpack into an xv6 directory, and then I can just do the same thing but with X instead of T. By the way, you can see I'm pretty comfortable editing. Any modern shell that you're using will allow you to edit previous commands, and you should absolutely be doing that instead of retyping the same thing over and over again. By the way, anytime in life, in computers, or in life, I really mean in computers when I'm saying life, which is already kind of sad, but anytime in computer world, if you find yourself typing the same thing over and over again, you are doing something wrong, okay? That's like a law of computing. If you are doing the same thing over and over again, you're doing it wrong. Why? Because that's what computers do. Doesn't that it drives me crazy? I'll see a student type like the same long thing in 500 times in a row. I'm like, do you know that computers are good at that? And they're like, no, I didn't know that. So, but that's none of you, of course. I always blame students in general, which is kind of mean, but really most of you are very clever, so you wouldn't do that. Okay, so I unpack it, I CD, I change directories into xv6, and then we have the xv6 subdirectories that we've organized to make it a little bit easier to understand xv6 instead of putting it all into one thing. Yeah?
For our accounts, does it matter which directory we unpack it into?
Oh, when you're working on it, you mean? No, you can do it wherever you want. probably important things to do are to be aware of things like privacy controls. So there's a link off some project webpage somewhere about that. Don't, like, for example, go into your public HTML directory and do all your work in there, because then someone could actually, anyone on the internet could see what you're doing. If you go into your public directory in general, and so what I would recommend is there's a private directory that's in the top level of your like CS accounts when you log into those machines, and if you just create something in that private directory, it will do the right thing. Otherwise, you can use this fs. How many people have used this fs command before? All 0 of you. Well, you can do things like list your access control lists, which means like basically list privileges on this directory. You can see this lets me do a bunch of stuff. I actually have a default where I let my wife look at any directory I have, which is a little weird, but it turned out to be convenient as opposed to strange. And then you can see system administrators have right to do everything, which is true in a lot of systems, which led to the NSA to some recent problems, actually. If you've been following the news at all, letting administrators be able to access everything that you ever look at inside of a security organization might be a little strange. But anyway, you can change that. You can do things like, oh, let's say I want to let my TA be able to look at this directory. The TA, one of the TAs is Brandon Davis. I can let him say read and list things in this directory. So just if you're interested in that, great. If you're not, that's fine. Just go cd into private and then make a directory in there like project 1 and then work inside of there. Okay. Anyway, what we're going to do now is simply do what we would do naturally when we unpack a source code thing, which is, sorry, I need my, just type make. I need my clock out. Oh no, I have a clock right there. In fact, I hear it every minute. Okay, and you can see it builds. So that's pretty exciting. And then we can do things like we can go ahead and run it by typing make qemu, or which is the emulator. Qemu again is just a program that basically boots like a real system, a real x86 system, and then emulates it in software. So it's really slow, but it makes our life much better as kernel developers. When we don't have this, we have to boot onto real machines, and when we make a mistake, we have to go power cycle it. Life becomes horrible, right? So the invention of all these emulators has made kernel development much more palatable, and virtual machine technology if you use that at all. So anyway, we can go ahead and run that, and you can see it boots up, and we can type all sorts of things like ls, because that's what else can you do in this xv6? Not much, it turns out. Okay, so then I just kill that window there, and we're done. We pop out of it again. So now what we're going to do is we're going to start the path of understanding how we get from a user program all the way into the kernel. And of course the path back is just unwinding all of that. We'll do that too briefly, but mostly we'll focus on going into the kernel from a user program. Okay? So does the system call as a concept make sense to everybody? If that doesn't make sense, the conceptual thing is really much easier to talk about, right? You're like, oh, there's a trap, there's a few instructions, you go in, you save some state, you come out. Then when you start looking at the real stuff, there's a lot of detail, like there isn't anything in the world. That's why we do these projects, so you can see a detailed real thing as well as hear about the conceptual piece. It's supposed to marry, theory and practice, right? Operating systems theory. But in any case, it's much more detailed, and so you have to pay a little bit of attention. And we'll skip over some things, of course, because some details you don't need to know. And what you're always trying to do when you're doing a project like this is figure out at some level, as an engineering mind, is figuring out what details do I need to figure out and really understand versus which ones can I kind of gloss over for now and leave for later. So that's always something you should be thinking about. Now, of course, you're a student, so you have the great pleasure of, having lots of free time, at least as I remember it. You probably don't think of it that way now, which means you can go and learn about things that even aren't that necessary, and it's probably fun. Okay, so here are some directories. The important ones to look at here are the user directory, where we're going to have user programs that we're going to build them in there, like ls and things like that. And we're going to, of course, make our own program maybe to test this kernel in there, like whatever you want to call it, test1 or something, .c. And we're going to compile user programs in there. And they're going to make system calls. So somehow we're going to have to connect them, get them to issue like a trap instruction, and hop into the kernel. The kernel is in here. Okay? So that's an important subdirectory, and we'll look at that in some detail. And of course, there's some files in here, include, which are shared across some places. So we made that. And then there's some other places you could look at too, but that's most of the stuff we need to worry about for right now. Okay, so let's go ahead and start looking at some things. Let's look at user. I don't know what we should look at. well, here's ls. Ls is my favorite program, is what people think after this course is over, but that's not true. It's just one of my favorites. Okay, so here's ls. What does it do? It lists some files in a directory, and it does that by doing a bunch of system calls, so that's not too exciting. Here's the main. In fact, here's another system call that main makes. It's exit. You know, when it's done, it says it calls exit, and that's just. In fact, you'll notice all the xv6 programs don't just return. They don't return from main. They actually call exit, and if you don't put an exit at the end of the main program, one student already ran into this. Something slightly weird will happen, and we'll talk about that later on in the semester. You can figure it out if you want. It's kind of cool, but always end a program in xv6 with an exit, which is a little strange. But exit's a system call, and what exit does is it tells the kernel, I'm done. You can, it's like, you could call it like suicide, right? It's kind of a sad system call. I'm all done with everything I ever wanted to do. I'm just going to exit now. So what we're going to do now is figure out how does this, what looks like a function call here, it looks like, right, when you look at exit, somebody, if you know C, you say that looks like a function call, and it is. But eventually it becomes a trap instruction, which in x86 is called int, for interrupt, which is confusing, and which will get us into the kernel. Okay? So that's exit. So let me pop out of this for a second. Let's do something like this. One way you can learn about any program you have is you can learn by seeing how the program is compiled or built. Okay? That's a really good way to see like what else is kind of being sucked into this program in order so I can understand better where some code is coming from. If we just look at, in fact, let's just make our own program. Let's call it user hello.c. Let's start with something like ls to begin with, but we don't need all this stuff. Maybe we need these things. And our hello world doesn't need to do very much. It'll just exit, and maybe it'll do this too. I'm sorry. So it'll printf hello. And we did this, I think, maybe last time. And in fact, it might say, hello, my name is, and we'll pass in an argument. Okay? argv0, what's going to say? Hello, my name is? Yeah, it's going to say hello because that'll be the command line when we compile it. Okay, so here's a simple program. Now in the user subdirectory here, which you can see I'm playing with because you can see this piece right here, there's a make file that if you're going to add a new program, you better go and play around with. So I'm going to go do that. You can see here is a bunch of user programs that get built. I'll add hello into that list, and then I'll save it. I don't have to really look anywhere else in this make file to see that that's done, and then this looks pretty good. A couple includes. One point of confusion for previous students. The types of things you include in these xv6 world is going to be a little different than actually what you do in Linux in real world. So the worlds are very similar. They look like C programs and they look like they're in a Unix environment, but they're slightly different. So try not to be confused, but it's going to be confusing for some of you. Okay, so let's type make. Okay, built, and we could run it, but well, why don't we run it just to make sure. Oh, in fact, there's this, no, I won't run that mode because it's a pain. So I could type hello here, and hopefully it says something reasonable. Hello, my name is hello. argv0 is the name of the executable. Okay, so it works, and I'm not yet a liar. But we saw here how it was built, and this is kind of interesting. There's a little complaint because of that, but let's ignore that. So you can see the first thing is done is this line here. Now lines that come out of make files, how many of you are familiar with make files? Some of you. Okay, good. So if you're not, you should start to get familiar with them. That's going to be my answer about everything. And one thing you'll see coming out of makefiles is there's like GCC when people run it. They don't just write GCC and then hello.oc or whatever. They have a lot of flags, like for example turning on all warnings and turning those into errors, and some help for GDB, and don't make position independent code, and don't use any built-ins, and use don't do any strict alias. There's all this stuff that they do. Don't turn on the stack protector, which is a security feature. Build a 32-bit binary, not a 64-bit binary, which might be your inclination, and so forth and so on. So that part I'm not going to care about. And you have to kind of learn not to look at those things when you're trying to understand what the makefile is doing. Those are just flags, and you can assume whoever made the makefile had a reason for all those flags. And so when they compile every C file of that type, they're going to probably use those same flags over and over. Here all they're doing is they're compiling, amazingly, hello.c, and they're turning it, into hello.o. Now the next line is, or sorry, that happens here. And then what's interesting here, and the line I want to point you to is this one. It's a line with LD at the beginning. So what is this line doing? What is LD? Does anybody know? It's called a link editor, or you might just call it a linker. What it's doing is it's taking like hello.o, which we've compiled, which is actually just taken our C code and turned it into what's called an object file. The object file has all the basic, assembly instructions and things like that in it, but it's not connected yet to functions that we're interested in outside of it. Like when you call printf, for example, when you write a program, you don't have to actually write the code for printf. You link with it. Someone else wrote it and you link with it, right? It's in some library somewhere. And that's true here in xv6. In fact, you could look at their printf implementation. In fact, in user printf, you can see right here that you're going to link with their printf, and you're going to link with their user level malloc library, and you're going to link with this generic user library ulib, and then kind of interesting, you're going to link with something called, in the user subdirectory, called usys, and it's called .o because it's an object file, but we'll look at it, and that's where all the system calls are, okay, in usys, and it's actually usys.s, which is an assembly file, because as we talked about in class, while when we call exit or open or read or any of the system calls, it looks like a function call, because it jumps to a function, but in there it's just some assembly instructions to do some setup and then to trap into the kernel. So it has to be written in assembly, because eventually you have to do an assembly instruction, which C isn't support like arbitrary traps. You have to just say at some point, I'm going to do this assembly instruction, which is trap into the kernel. Does that make sense? Obvious? Too slow? Okay, I do things too slowly sometimes. For that, you will forgive me. So what we're going to do now is we're going to look at the user directory, and we're going to look at usys dot. And you can see .s is the thing we have to look at, because it's an assembly file that's going to take us into the kernel. Now, let's take a peek at it. Okay, sorry, let me scoot down a little bit. So what you see here, from syscall, this first syscall thing here to this last one, are all the system calls that exist in xv6. There aren't many. It's like, what, 20-some? I can't remember how many. Fork, which we'll talk about fork when we do the next project. It's a way to, in Unix, to create a new process. Exit, which we are going to follow in some detail. Wait, which is wait for a process to complete executing. Pipes, read, write, close, file system, things like that. Some other things, okay? A bunch of system calls. And we'll learn about more of these as we get into the semester, as we learn about different parts of the operating system. Now what's a little bit funny here is, to understand this code, you're going to have to actually understand how macros work in C world. And you can see they've defined a macro called syscall, which takes a name, like fork, for example, or exit. Let's say we're interested in exit. And then outputs this code. Basically, it puts this .global thing here, which is a way of making sure that like a name can be known. And then it says for that entry point, like for fork or exit or any of those, actually just put these 3 assembly instructions. Okay, it just does 3 assembly instructions is what each of these macros generate. Okay, so in fact, if we remove, let's say user usys .o, and then we make something. Of course, a lot of stuff happens because everybody depends on usys.o. But you can see one thing that in fact, what we could do is we could do this. Let's see if I have enough flags here. So if I compile with GCC with -S, it'll produce the assembly instead of trying to make an object file. And you can see what those macros end up looking like. They end up being .global. Here's a this fork entry point, and then here are these 3 instructions: move some number into EAX, call int with some value of the syscall, and then return. So let's look back at that again. So you can see those same 3 instructions kind of right there, if that makes sense. So all these instructions are doing is something very simple. For each system call, they're moving a number into the register EAX. EAX, and you have to remember this, is one of these general purpose registers in x86. It's used in a few cases, it's used in a special way. Does anybody know sometimes where EAX is used in a special way? Well, that's where it comes from. That's the historic name for it. It's not actually used as an accumulator anymore, and as are the other named registers aren't used as anything but general purpose. It's actually used for return codes. So when you call into a C function, sometimes you need to type int, when you've defined a function, int foo. When you return that int, in x86 it's a convention to pass the return code in EAX. Okay, so in other words, if you have something valuable in EAX and you're about to call a function, what do you do usually? Yeah, you save it first because you know that the function will overwrite EAX with its return code. When I'm talking about calling conventions and call and return, are people like, oh my God, I think I was supposed to have learned about that? Or, oh yeah, I remember all that stuff, it's really easy. Where are we in that spectrum? Like, I've heard of it, I've never heard of it. I've heard of it, but I don't remember a lot of the details. Some. I've heard of it, and I pretty much understand what's going on there for some architecture. Okay. So we'll have to kind of remember a few of those details. And for this project, it's not super important, though it's useful. How much time do we have, by the way? 2:10. Okay, we're fine. For future projects, there will be a few places where you need to be a little bit careful. Of course, we'll go through the x86 piece in some detail, but it's good to start refreshing at that level a little bit for a few projects. Anyway, what we're doing here is we're moving the system, some number into EAX. And the reason we're doing that is for each different system call, we're going to want it to be the case when the kernel wakes up, when the kernel starts running, and it says, oh, this is a system call, we want to know which system call it is. So it can route the trap, essentially, to the right piece of code. Does that make sense? And does it have to be done this way? No, you could have done it in a million different ways, and Linux does it differently. Every operating system has its own convention for how you should tell it which system call you're executing. The xv6, the MIT kernel that we're playing with, the xv6 convention is put the system call number in EAX. Okay? Now, when you're making a system call, there's some other stuff you'd have to specify too, like what? Other than which system call, what else? When I open something, when I look at here, let's say I open a file. What do you notice about open? Is it just, hey, open something? Dear kernel, please open a file. What would the kernel say to you? Like, which file? Yeah, it needs arguments, right? It needs arguments. Now, when we're looking at this code, it's not dealing with arguments at all, right? So that might make you a little bit curious. Why are there no arguments? I'm not messing with arguments in here. What xv6 does, and again, this is by convention for this kernel and may not apply elsewhere, is it leaves those arguments on the stack. Basically, when you call this function, right? You remember you're calling a function, like we call exit or we call open. When you're calling those, you're pushing those arguments onto the user stack. What xv6 is going to know that they're sitting on the user stack, and it's going to assume that they're in there, and it's going to pull them off of your user stack to use them as arguments. Does that make sense? So they're just sitting in memory on your user stack, and so it doesn't do anything special. Other systems do different things, like Linux will pass some number of arguments in registers because it's faster than going to memory. But here it's simple. So all we have to do is push the number into the system call into EAX, and then we issue our trap instruction. Okay? Very simple. It's an instruction that takes one argument. That argument is actually a number, though here it looks like $T_syscall. That number is actually like 64 or something. That's a convention too. The xv6 people said, let's use 64 for system calls. And that's going to help us route it to the correct trap handler. Like if you put a different number there, it will execute some different code as specified by a different trap handler. Because we have a number of trap handlers we're going to set up. Okay, that's it. This is a super amazing, powerful instruction, right? We call it, and then a bunch of stuff happens. Some state is saved. We'll talk about how that happens. We hop into the kernel. We go into kernel mode. We start executing inside the kernel at one of these trap handlers. Eventually, it figures out which and routes it to the right thing, which does some work on our behalf, like opens a file or whatever, and then slowly comes back and returns to us. Okay? And it's also implied by the way this is all set up that when we return, the return value will be an EAX. So whatever system call will return an EAX, and then this return, which is just, this is a normal function call return instruction. That will, do some stuff for us, which is what x86 return does, but it'll also presume that EAX has the return code of the system call we just made. Any questions about that? Sound horrible? Okay. Sounds great. What is it? Where are we? Fine? All good? Okay. Question? Just okay. All right. Well, it's going to get much worse in a second. So any questions about this now that you know it's going to get much worse? This is the easy part, right? I just about 3 instructions, right? It's like move a number into a register, trap into the kernel, and then, of course, return from this function. Okay, great. So obviously, if you're adding a system call, one thing you're going to do is you're going to do something in here. In fact, I bet you can guess what that thing is. You're going to do something like syscall, my favorite, system call, right, or whatever it's called. And it's going to do all the right stuff for you. They've already set up the macro to be kind of set up to do the right thing. One other thing on the user side of the world, which is one thing you might want to do when your grep is really useful because you get to kind of poke around a code base. It's a very primitive way of doing that, but let's just use that. You can see there's also this file called, capital H. Capital H in grep tells you what the file name is. There are other ways to do that too. But in any case, what you can see here, there's this file called user.h, and we should look at that too. That's the other kind of last other file we care about. What it does is for each of the system calls, it basically just describes their signature, or in other words, what they return and what parameters they take, which might include void, like no parameters. Like exit, for example, on xv6 takes no parameters. A typical Unix exit will take a parameter, which is like your exit code. You can see write takes a few different ones, whatever. So when you're adding a system call, you're probably going to have to add one of these. And what these do are they help the C compiler. They say the C compiler, oh, this is what this should look like. So when somebody calls exit or calls open or calls unlink in their program, I can kind of check, are they passing the right arguments? And if they're not, I can complain and prevent them from building it. Okay? Makes sense? This is just kind of a C thing. Okay, that's user side. Let's go into the hard part, kernel land. Kernel land is more complicated. There's a lot of stuff. Of course, you could just start at the boot code and see, hey, how does everything boot up? And if you're interested in that, booting is like one of these mysterious things. Starting up a computer, what happens? It's actually not that mysterious, but because it does like what a computer does. It follows some very prescribed set of actions. You can sit here and stare at all the assembly stuff that happens to initialize the machine. We're not really going to do that, and I don't have a good project that relates to boot code. You'll probably thank me for that at some point. What you can eventually learn is that we get into some code, called bootmain.c, and eventually that's going to call into something called, and I'm going to skip up most of this code. That's going to eventually get into into main.c, and eventually that's going to get into a routine called main.c. And this is only run on one processor if you're running in a multiprocessor, and then there's some initialization that's done on a few other processors as well if you have multiple processors. But this code is actually, at some level, easy to understand because what it's doing is it's saying, oh, I have an interrupt controller, and we'll talk about how those things work later on in the class, but I need to initialize it. There's another one there. Great. There's something with the console, need to initialize that. Oh, I need to initialize the serial port. Oh, I need to, there's this thing called a kernel page table, which is going to be used for virtualizing memory. I need to initialize that. So basically, remember we talked about there's this kind of generic protocol we have in the kernel, approach to how we do things, which is when we boot, we set a bunch of stuff up, and then when we run, it kind of prevents user programs from doing bad things. This is going to be that part of the kernel where this stuff gets set up. Does that make sense? Okay, so one thing we're going to look at here is these trap vectors, because one thing we know has to happen with xv6 and being able to handle a trap is somebody has to tell the CPU where those trap vectors are. In fact, you have to tell each CPU about it, but that's what we're going to do here. Okay, so we're going to look a little bit at that code, trap.c, and it's called trap vector init, tv init. And you can see it's right here. And it's actually, this is the whole piece of code right here. And of course, it doesn't look, it looks like kernel code. which is unpleasant. And what it does is, well, you don't have to really know what it does. But what it does is, if you want to look, it actually uses this macro here called setGate. It actually uses this macro to describe x86, the hardware, has a very specific way it wants you to tell it about where trap vectors are. And it's not nice looking. It's this memory layout with all these bits have to be in certain places in certain ways, because when people built these processors, they're very bit oriented. So they don't like say, hey, let's make a really nice interface to this. Let's just say, here are the bits and here are how they've got to be in memory, and then tell me where it is, and that's good enough. So if you're interested in how all that stuff gets laid out, you can find the setGate macro, and the way you would find it is, let's say, something like this. You can see it's in kernel mmu.h right there. And if I go ahead and do mmu.h, you can find a bunch of, all this C code that's really a lot of fun to look at. But you can see that there's a lot of stuff in there. But here's this macro, and what it does is it basically, you call it and you give it some information, like here's where I think the trap vectors are, and then it lays it out into the exact structure that the hardware needs. Like these bits need to be in these exact right spots. Now you're just putting this in memory right now, but eventually you're going to tell the kernel about where that thing in memory is, and it's going to use that to know where the trap vectors are. If you do this wrong and you get one bit wrong, what's going to happen? Nothing's going to work at all. So thank God somebody did this for you, right? If you're doing it from scratch, it's like the most frustrating, painstaking stuff you ever do, because you get one bit off and the system doesn't work, and it doesn't tell you, print out, you got this one bit doesn't make sense. Did you know that? It just doesn't work. It hangs, or it blows up. It probably doesn't blow up. It probably just hangs. It probably doesn't do anything. So anyway, this is where they're setting up the trap vectors, and you can see in particular there's this one for the system calls, and there's this important piece of that, which is this array called vectors. These vectors are just an array, basically, of a little bit of what each trap vector looks like, which is what we're going to take a peek at in a second. Okay. Now, it turns out that TV init just sets these structures up in memory, but the CPU still doesn't know where they are. You have to tell the CPU. And to do that, later on, this routine IDT init is called, which is interrupt descriptor table init. And what that does is basically, what it looks like it's calling this function LIDT, but that's actually a macro for an assembly instruction, which is called LIDT, which is telling the hardware this is where the interrupt descriptor table lives in memory. So remember we talked about that in class conceptually. You have to tell the hardware when you boot, here's where the trap handlers are, and then later on when you do a trap, it knows what code to run. This is that code. And you can see why we don't talk, or at least why I don't talk, about the specifics in class, because you start staring at it and you get obsessed with all the wrong things, like why are they shifting seg k code by 3, and what's a DPL user mean, and there's all these details which you can go read about now, but you'll have the conceptual framework, and you don't have to read about it for this project, but you'll have the conceptual framework in your mind of what they're trying to do, or you should. If you don't, then you probably miss lecture. Okay, any questions about that? Kind of makes sense? So we have to figure out where these vectors are. And you look at this very handy comment. This is, by the way, an example of a useful comment. Where are these vectors? They're in vectors.s. Okay, good. Let's take a look at that. It also even tells us it's just an array of 256 entry pointers. So at the bottom of vectors.s is basically for each vector, it says, here's a little piece of code you need to run. And you can see there's a bunch of them. So this is defining this vector array here. You can see here it's defined in assembly, like in a .s file. But those are just going to hop up to a little 3-instruction sequence. And so for each vector, including the one that's the syscall one, which is 64, I believe, which we'll look at, but it's pretty much the same. It says when I get an interrupt, which is a trap 64, which is for system calls, do a couple instructions here, and then jump to this routine all traps. And you can in fact see in xv6 the way they've set it up is every trap or interrupt you get is going to all route through the same place, which is the all traps routine. And we'll take a look at that in a second. This pushing of stuff we don't have to worry about too much right now, but we'll take it. Basically there's some stuff they have to put on the stack that we're running on now, and in order for the trap frame to be fully built. And so this is the first piece of that. And one of those pieces is which trap is it? And we know this is trap 64 or interrupt 64, however you want to call it. and we're pushing that number onto the stack, and later we'll use that to know that this is a system call. Push is very simple in x86 world. When you push something, whatever the current stack you're using, it'll put it on the top of that stack and decrement the stack pointer because stacks grow backwards. Okay, so let's look at the all traps code a little bit, which is in trap asm.s. We're still stuck in assembly. So every trap in the world in xv6 is going to be routed here. And what it's going to do is it's going to complete building what it calls a trap frame. So now we have to understand a little bit about what's going on. When we trap into the kernel, what's happening? Well, the hardware, remember we said the hardware does all this stuff. It moves us into kernel mode. It does a few other things, right? That's a major thing that it does. It's going to route us to this code eventually. But one thing it also does is it saves a little bit of state. Because when we trap into the kernel, we have to know where to go back to when we're done, right? So like the program counter is something that the hardware is going to save for us. Now the question is, where do you save that stuff? So we have to save the program counter, but where are we going to save it to? Yeah, you could save it on, in fact, the same user stack you're running on. Most modern kernels won't do things like that because they view that user stack as I don't want to be trusting that too much. So what they do in x86 generally, and xv6 very specifically, is they basically assume that each process that's running, not only does it have a user stack, which you use when you call functions and so forth, but it has, when it gets created, a kernel stack associated with it. So when we trap into the kernel, we actually switch from using that user stack to we're going to start running on this per process kernel stack. This is a lot of detail and it can be somewhat confusing, but I'm just telling you so you have some basis of knowing. You don't have to know a lot of this to do this project. But it means right now when we jump into the kernel, some stuff has been saved onto that kernel stack, like the program counter we're going to have to hop back to. And then there's a few things that we're going to have to save ourselves if we care about those register values. So all they're doing at this first part of all traps is saving a few more registers onto this, what we call a trap frame. That's just all the stuff that we need to save when we trap. Does that make sense? Kind of. And if you want to look at the trap frame, what all the stuff that's inside of it, it's in include x86.h, and it's somewhere down here, I believe. Yeah. And you can see it's called there's a structure called trap frame. The bottom part of it is defined exactly by hardware. And all that stuff gets pushed onto the kernel stack when you trap into the kernel. The rest, like the trap number and a few other things, all these other registers, like the general purpose registers and the stack pointer, the user stack pointer and the user base pointer, all those get pushed on by the software itself. So there's a bit of a combination there. The kernel pushes some stuff, and then we push some stuff. So all traps does is save some more state beyond what's already been saved so that your registers don't get clobbered. It does some stuff with segments, which has to do with memory management. We're not worried about that right now. And then it basically just calls into a C-level routine, which should be for you a great relief. If you're following along at this point and your eyes look heavy and you're like, he keeps making me look at assembly, what kind of horrible person is he? At this point you can be relieved, or you can wake up again, because we're back in C code. And C code is actually what you'll be dealing with. And you can see this C code is actually fairly easy to understand. It says here's a trap and I'm going to pass you the trap frame. So if you care about anything that's saved in there, good for you. You can look at it. And here's in fact where we're going to generically handle system calls. And you can see what it does. The first thing it does is it says if the trap number is T syscall, then this is how you handle a system call. In fact, what it does is it checks, is the process killed already? If so, exit. If not, set basically the current process's trap frame, so to keep track of what the current process is, it records its trap frame, and then call this generic routine called syscall. Okay, that's it. And when it's done, it checks if it's killed again, and then it returns. And then when it returns, it undoes all that stuff. Now this is kind of a cool piece. Remember we pushed, like long ago, we pushed like some number into some register, like the trap number got pushed into that trap frame, and now we can start pulling those things out to see what to do. So to understand one last piece of this chain, you probably have to understand the syscall code, and that's right here, and it's also very simple. It's every system call is routed through here. If I'm writing I want to change the kernel to count system calls, One very useful thing might be to know here's some generic, high-level, easy-to-understand C code that actually every system call is routed through here, right? So how helpful is that? And this is checking a few basic things. It's checking, like, is the system call number, which is ends up putting it into this thing num here, is it greater than 0 and less than the total number of system calls? So you can't just give some arbitrary number and then hope it works. And it wants to make sure that this system call table, which is actually up here, which has pointers to functions, which we'll talk about in a second, that it has reasonable things in it. Now here's this kind of interesting thing. What is it doing with this piece of code right here? Yeah. No. I mean, just from a C perspective, what is this doing? This is looking in a struct called proc. That's what you just guess that by looking at that. For an element called TF, which we know is the trap frame actually. And if we remember going back here, remember that like proc.tf was set to the trap frame that got passed into trap. And if we remember trap asm.s, we remember that that basically gets called with the trap frame as an argument. So we've set up all this register state of the user program gets saved into this trap frame, which is in a kernel stack. It's in kernel memory somewhere. And then we call trap with a pointer to that structure. Then it sets proc trap frame to that and then calls syscall. Then, then it pulls something out of that trap frame. It pulls, in fact, the value of EAX. Why does it pull that out? Because that's which system call we were doing. Remember long ago, that was so many years ago, when we were looking at user code and we were happy and we thought this was going to be a fun and short discussion. Remember those days? And what you might remember about those days is that we moved a number into EAX in user code. So we've gone all the way through and we're all the way in the kernel, and finally what the kernel says is, oh, what's that number? And then it can decide what to do. In fact, what it decides to do is it uses basically this C function pointers to call, it takes a table of function pointers, so that's the syscalls table, which is just above here, and we'll look at it in a second, indexes it by the number and calls that function. And then the return value, as you can see, remember I promised you return values are passed in EAX2, it puts back in that trap frame, and then when it pops out of the kernel, it's going to be in the register EAX in your user program. Does that make sense? Kind of? Yeah, it's kind of interesting. You can study it and it'll make more sense. There is no learning without pain, as I like to tell people. They're like, why'd you get into teaching then? And I'm like, I don't know. It sounded better at first. No. So anyway, here you can see we have the syscall table, and you can see a bunch of things. But basically, like if we want to then know what function, it's basically, if this is a number over here, like system call sys_chr, which let's say is number 8 or something. Call this function sys_chr. And if we wanted to learn where exit was, for example, we could then grep for sysexit inside the kernel. So inside kernel star.c, and you can see it's in sysproc.c. Then we could go ahead and open that, and we could find sysexit, which you can see calls exit, which might be in here, which might be somewhere else. I don't remember where exit is. And you can see that's in proc.c, which makes sense. And there's some organization to these things, and at first you'll be like, where do I add code? And you'll get it wrong at first. That's fine. And you can see this is what exit does. And exit does a bunch of stuff, like it, for example, closes all your open files and does some other stuff which we don't have to worry about, but removes it. Remember we talked about there's a process list, and this is a process table actually. It removes this entry, or actually marks it as almost dead. There's this other state called zombie, which is you're dead but nobody knows about it yet. And then it calls back into the scheduler to schedule something else. So that's the work of exit. So anyway, all the way back to syscall.c, you can see that this is how system calls are handled. And then we can go all the way back through and we'll undo all those things. And when we finally do one last instruction, remember we said there were 2 special instructions. In x86 there's an int instruction, which is called interrupt, but I call it a trap to confuse you, that gets us into the kernel. But we need another special instruction that gets us out of the kernel and restores us into user mode and does all that fun stuff. And that instruction has to happen at the end of this trap ASM, and you can see it's called IRET, or interrupt return on x86. So that's a very special instruction. It undoes all that stuff. And that is more or less how we get in and out of the kernel. What timing is that? Where's the applause? So anyway, I'm going to end that right now. I'm going to stop recording. If you have questions, I'll stick around for a few minutes. I unfortunately can't make office hours today because my kid has to go to the orthodontist. If you want to meet, I have one tomorrow, or I can meet Friday too.